Thank you for joining me today, and I will be talking about fuzzing file system implementations, especially in the context of BSD operating systems. Originally, this was planned as an interactive lab session on site, but since we cannot do this, I kind of revamped the content to be in a general walkthrough how-to guide with some demos and proof of concepts on how you can approach such a topic. So let's get started. First, who am I? I'm Christopher. You can find me on several social media channels, for example, Twitter. If you want to reach out, feel free. Basically, I'm a security researcher at Fraunhofer FKIE in Germany since last year. And my interests in general are the Unix side of things, IoT, reverse engineering, exploit dev, and obviously fuzzing. So yeah, let's get started with the actual content now. First, I'll try to cover a couple of whys, like why is this topic interesting, why should we look into this, and maybe why should you look into this. Following that is like a general how you could approach this with some kind of demos. Last but not least, then some caveats, what to look out for when like trying to write your own fuzzing framework. And lastly, some results I could find and uncover on the BSD side of things. So let's get started. So why fuzzing, why BSD, why file system, and why not just use an existing tool? I'll get back to that later. So why fuzzing? Right now, we're kind of in a fuzzing renaissance. And everybody does fuzzing, and probably like every week or so, there's a new fuzzing tool coming out. So it's a new cool thing to do. Anyhow, fuzzing itself allows for deeply inspecting a project or like some code base, because you have to optimize your algorithms to get deep into the code base to uncover bugs that are not just shallow on the surface. Also, manual bug hunting is not really scalable, since we are dealing with large code bases nowadays. You probably won't find bugs easily anymore. But I mean, if you do, it's really rewarding. But automating this kind of stuff with fuzzing is scalable. Last but not least, in my opinion, fuzzing itself is a fun thing to do, because on one side, you can like try to optimize your fuzzing framework if you're not just like throwing an existing framework on some kind of problem out there. On the other hand, you learn a lot about tooling, engineering, and actual internals. So that's why I decided to go with fuzzing. Next up, why the hell should we look at BSD? There are a few arguments for that. First, in recent times, there's like a lot of systems running BSD, or like getting some code bases from BSD. For example, if we look at Sony, their home entertainment lineup, the PlayStation uses the FreeBSD kernel. There's server infrastructures running on FreeBSD, for example, from Netflix or WhatsApp. And even the macOS Darwin kernel has functionality from the BSD kernel. Yeah. I mean, nowadays it's heavily modified, but it's still originally from the BSD kernel, among other stuff. Then again, I'm not really interested in the Windows side. So last but not least, everybody seems to do Linux, especially when it comes to Debian and Ubuntu. So my conclusion when researching this was not all systems were tested equally well. So as a follow-up from this, so why not check out the BSDs? So let's do this. File systems, you can probably divide them in three big parts, like a user land component, a kernel land component, and then the actual disk component. But in this talk, I want to focus on the kernel land component. Why is that? I will get to that now. So if you want to structure access to a file system from userland to the actual disk access in a flowchart, you probably start with some kind of userland interaction with which interfaces with a syscall interface to the kernel. In the context of BSD, and especially FreeBSD, which I will focus on now, there's a direct check if the file system access is to a UFS file system, which is native to FreeBSD. And if it's not, the control flow is redirected to a virtual file system layer, which handles all the other file systems. For example, ext, ZFS, among others. If it is UFS you're dealing with, there's a direct call to UFS-specific file system functionality. And then again, after the specific file system-specific handlers are called and code is executed, there's some caching and some device driver magic and following. And finally, there's an access to disk. So that's a pretty rough and high-level overview of file system access from userland to disk access in FreeBSD. If you want to look deeper into file system, you come across different structures like, for example, this is like a UFS overview about how it is divided into some form of cylinder groups, some groups within the cylinder groups like offset and superblock, cylinder group map, inodes, and so forth. Just keep in mind for now that basically what you can see here is that a file system itself is just a large binary block that can be divided into chunks or is divided into chunks where different metadata and actual data is stored itself. So it's nothing too fancy. It's implemented complicatedly, but it's still okay. If you look at another structure, same stuff. You have chunks, you have metadata chunks, you have chunks with data in them, and you have probably some fields which have pointers to data or pointers to pointers which point to data fields. This, for example, is the ext structure, and this is the ZFS structure. As you can see, it all looks heavily different, but in the end, it boils down to it having it's being divided into different chunks, which hold some metadata and some data. So when you're looking at file systems, you can notice the following when doing your research. File systems are often overlooked in security research, and you can look up some publications on Google Scholar, and you won't find many. However, in my opinion, when you're dealing with data and critical data stored on a file system, at least the availability should be ensured and tested for, if not integrity and confidentiality too. Additionally, nowadays we're dealing with a lot of file system in our daily lives. Just imagine the usage of USB drives passed around with some data to be shared. But what if the underlying file system on these devices is malformed or tampered with? Because ultimately, accessing file systems or writing or reading to or from file system means kernel code execution, as seen in the high-level overview. Finally, the last wide question for now is why not use tool X for kernel fuzzing, as there are some tools for kernel fuzzing out there, especially famous one like syscaller. After doing my research, none of those really fit my needs. I was interested in the complete execution chain, as I call it here, which means I want to actually do the whole metadata parsing of file system, try to mount file system, access them, modify them, and finally unmount them again from a system. All these steps can be vulnerable or prone to errors within the file system, within the operating system, because all these steps need kernel code to be executed. And if some of them are trying to parse malformed binary blobs within the file system, obviously there can be a crash. So it's interesting to look at those. So how would you go about writing your own kernel or file system fuzzer that uses kernel code? In my opinion, you need around 6 necessary steps to do that on your own, which I had intended to teach you in a lab session on site, but let's do this virtually. First of all, you need to think about how to create test cases in the first place. What mutation do you apply? Do you go for like single byte flips? Do you go for full binary mutation? Or do you try targeted mutation at different metadata fields? What do you do? Then again, if you want to write a framework, you need to monitor the expected or like the seen behavior somehow. And you need some kind of logging to see what's going on in such a exclusive environment like the kernel. Finally, in my opinion, you need to emulate a user when dealing with file systems. I will come to that later. Like I will extensively talk about what I mean with that. And finally, you want to verify and optimize your results, obviously. So let's start with the first step, create test cases. When doing this and looking for bugs in file systems themselves, what do you need for a test case? In my opinion, it's an actual disk image you can use. And for that reason, I wrote a little helper script that lets me generate populated or non-populated file system with variable sizes automatically. And currently, I'm able to create UFS version 1 and 2, ZFS, different EXT file system, and APFS. One observation made here was that you can, when writing your framework, you should avoid a different host and target OSs because this can cause major headaches. And generally, I will always include some kind of flowchart on the slides when dealing with these different steps needed. So in this case, the framework should probably read some config file and based on that config file, generate the file system and as seen on the right, hopefully. Let's demonstrate this. I'm on the server here. Hopefully you can see that now. So if you do, you can like run this little helper script and let's, for example, let's create an UFS version 2 file system of size 10 with the name, let's call it hack in the box UFS. Let's correct that. And let's output it to the current working directory. So as you can see, the script just outputs that it created an empty file system called hack_UFS. That's because the Ubuntu or Debian kernel is kind of clunky with like dealing with the UFS file systems. It can't really access them properly and write to them. So that's a little bit weird, but as we can see, if that's working. Okay, as you can see, it at least correctly created an empty file system. You can see on the timestamp it was just created. But for the next, like when you're dealing with file systems and trying to think about real-world scenarios, you not really encounter empty file systems that often. So you want to probably write some data to it before mutating them. For that reason, I extended the script so you can do the following. But since UFS is a little bit weird on Debian, let's go with the ext file system, and why not go with the ext4? Let's adjust that too. And let's say we want to create 10 random files, each with the maximum file size of 1 megabyte. And if that's working, okay, seems to have worked. The std out for this script is kind of verbose, but bear with me here. So as you can see, there's a seed value for each file generated from 0 to 9. The seed value that is randomly generated is seen here. And this seed value actually controls the whole file. What I mean by that is this seed controls the file name length, and what kind of file it created and where it's placed. In this case, this seed decided the file should be a symlink out of a hard link, directory, binary data, or symlink. This is the source file. The file path and the file name and so forth. And as you can see, this created, like, for example, this one created a file with about roughly 0.5 MB and placed it at lost and found and the file name. So with this script, we are easily able to create test cases. We can check this again. Let's see. As you can see, it actually created an X4 file system. So with this at hand, with this tooling, we can already create valid test cases which are populated, and the structure and underlying geography of the file is controlled by us. So we can play around with that a lot. And this is extremely helpful as in the first step for us. Okay, let's get back to the slides. Next up, mutation. As I already said, how do you go about mutating file system? As I already told you as well, is that the file system itself is just a large binary blob with like a kind of complex structure. You can think about trying to mutate different fields and bits and pieces. So for testing purposes, obviously we can just try to zero out, FF out, randomize different blocks like the super block, which holds the metadata, cylinder groups, or like single bytes, or like do even targeted mutations at specific fields you already know of. Or you can try a full binary mutation in the case for, like, let's say with Redenza, which is like actually working pretty good for those. And the observation to be made here is that these kind of super dump mutations are often enough to trigger kernel bugs, because nobody expects you that someone is just flipping bytes in a metadata field and then it's getting passed, or like when mounting or accessing the file system, and nobody expects you to do that with the malformed file system. So let's, in the case for the flowchart, it's probably fetch the test case from the test case generator, read the config file, apply the mutation that is configured, and then save the sample. That's pretty straightforward for the mutation part. But how would you go about that in like a heading script? So for that, I've prepared another one. So as we can see, this one we created earlier, the Unix fast file system, or UFS version 2. And we can just go ahead and do, for example, use this script, supply this file system. And let's say we want to target the super block, which is placed at every cylinder group at the beginning. So let's say we want to target the super block here, and we want to target all of them. And in this super block, there are specific fields, which you can read up on the documentary or like the source code itself. And there's one field called fs_fs mount. In the file system above, it's corresponding to the last mounted on. And in this one, it seems to be empty because it was created with not being mounted. So it wasn't mounted before. So we can just inject our own little code here. Let's say hello world at egg in the box 2020 lockdown. And let's output that to this file. See, okay, that seems to have worked as well. If we check with the file command now on this file, we can see we injected successfully our custom code in this metadata field, which, I mean, in this case, it only corresponds to the last mounted on, and it's not really useful, but it's just for the purpose of visualizing and showing that it works. And you can do this with every other field in the superblock. So if you we can use this little helper script, which passes the superblock in a UFS file system. And if we supply the one with the fs mount, there's some parameters missing, obviously. Let's take the first superblock and print it. You can see there's a lot of fields in the UFS superblock. It's pretty long and extensive for a lot of different stuff. And this field right here, this in hex is just the string we injected earlier. As you can see, there's also some magic bytes down here. And if we inject into magic bytes, you can easily find out that the file commander actually won't recognize it anymore at the UFS file system, because it basically just looks up this magic byte string from the first superblock. And if it's not present, it's obviously not a UFS file system, apparently. But the mounting command does the same stuff. On FreeBSD, if this magic byte is not there, it's not recognized and rejected flat out. So when like mutating file system, in the case of UFS, you have to ensure that at least the magic bytes are still correct. And we can test this with the same mutation script from earlier. We can mutate and do, let's take the original one without any modifications, inject into the first superblock again, this time into in the magic bytes. Let's do A. And then output it to magic. Let's see. Okay. We go to, if we check the file command, it just says data because it can't find the FS magic field corresponding to the UFS file system. It's wrong. Then again, if you check the superblock, you can see all the other fields are still intact. Whoops, I'm sorry for that. But you can see the FS magic bytes were changed to 4As. So this is one way for easy and simple corruptions, and you can automate this kind of stuff, obviously, and just test what happens. If we want to go a little bit more hardcore and just don't care about what happens to the file system, you can also go ahead and do like UFS, and we'll output it to this one. And we can do, I have implemented a simple redenser flag, which just takes the input binary, in this case, the hack-in-the-box UFS file system, and outputs the output to the argument supplied by the -O flag. And we want to, as a researcher, obviously, we want to have some kind of determinism. So you can just throw it into a redenser and it just does its magic. But what you want is like, you want to supply a seed so you can reproduce this result later on again. And I also implemented a restore flag, which after mutating it randomly, it at least restores the magic bytes. So let's see if that was correct. Obviously it wasn't, because it should be .py. Okay. So I randomly generated a seed which redenser can use, and the output redenser produced was saved to this file. Since we restored the magic bytes, the file command should at least recognize at a UFS file system, and indeed it does. From the output below, it seems to have, I'm not sure what it mutated, but from this output, it still looks pretty sane. We can do this over and over again and see what happens. You never know, because redenser just does some weird magic in the background, so you never know. But sometimes you're lucky and this one is completely empty and filled with zeros, for example, or some other crazy values. And then you can hope that when mounting and parsing the file system structure, you can hope for that it crashes, because nobody expected it to be that broken. Okay, that's it for the mutation steps. So what in my opinion, or like in my research, I was able to observe the following. In FreeBSD, when just throwing redenser on a file system, like only 20% of the produced samples were still good to be mounted, and 80% were flat out rejected by FreeBSD. And for the ext file system, it's like an inverse correlation. It's completely the other way around. And for ZFS, I've tested this too, and ZFS is kind of newish and has a lot of consistency and integrity checks in place. So this makes perfectly sense to me. that only about 8% are still getting mounted when applying Redenza mutation to a file system, because it can break so much metadata. And especially in the case for ZFS, there are like 4 scenarios. Redenza made everything horrible, and the pool, which ZFS calls the file system, is utterly broken. Then it's not recognized anymore, and it cannot be imported or mounted. Then there's either the scenario that some metadata is corrupted, it doesn't correspond to the data on disk, or the other way around, the data on disk is not matching the metadata that was saved. For example, checksums over data is calculated in ZFS, and if one of these don't match, it's like complaining a lot. And only in one case, if all of this is not the case and it's still a valid pool, and maybe Redenza just did a byte flip in a 0-byte area, and ZFS doesn't care about that, it's still importable. So what are the observations? For once, the inverse correlation between UFS and EXT, and I've thought about it, and my conclusion is that since UFS is native to FreeBSD, there's a lot of more consistency, or at least structural checks in place for this, for example, superblock or cylinder groups. And EXT is like more used on the Linux distributions, and it's probably put in place and implemented on FreeBSD because of compat reasons. So if you want to share data between Linux and FreeBSD, for example, and there's an X file, and if you can't mount it on BSD, it's kind of sucks. So it's probably implemented that for that reason. But there weren't that strict checks for the structure themselves. And as I already said, observation 2 is that the integrity checks for ZFS are kind of strict, and hence it only makes perfect sense that most of the samples mutated with Redenza are flat out rejected. But since this could be considered file system fuzzing itself, since we're like mutating and trying to mount them, and with this, we are like targeting the file system parser itself, at least the metadata parser. But what about the samples that are getting mounted? Are we just like ignoring them, or is there something else we can do about those? And this is where my research is kind of kicking in, because I thought, why not use some kind of user emulation where with those that are still getting mounted? So this is the usual scenario. We want to try to mount it and see if the target is alive. And if not, if the mounting fails, we probably, we always want to like go to the next iteration in our fuzzing framework, because the sample is bad and we can't mount it. If we mount it and the system crashes, we obviously have an error, and we have to, like, for example, restart the target VM and evaluate and analyze the crash. But what if the sample is still getting mounted? And there the user emulation kicks in. So this is the same stuff as before. And what I had in mind is, like, after checking if the system is still alive when the mount is successful, we're doing some initialization stuff, and then still check if the target is still alive. If not, there's some crash, and we can analyze the crash. But if yes, we basically loop over the command list and try to select the next command, roll the arguments for the command, run it, increment the counter, and check if the target is still alive. If not, there's a crash, and we can restart the VM and analyze the crash. And we do this as long as, like, our counter is smaller, or not as smaller than the length of the command list, obviously. And if we're running all the commands and there's still no crash, we have to do some teardown and maybe reset the VM, or like just jump ahead to the next fuzzing iteration. So what are those commands I'm talking about here? I thought about it and basically came up with the categorization and changing geometry, extending geometry, and parsing geometry. And for the changing geometry, I'm meaning those commands that take existing data and just change metadata from these. For example, if you change the execution mode or the owner, or like remove files from disk, is changing the underlying geometry of the file system. Then there's extending geometry, which just adds data to a file system. And parsing geometry is basically just parsing metadata from files themselves. For example, with stat or like file, as shown earlier. What you have to keep in mind is that all these commands from the changing geometry and extending geometry still pass or have to pass the underlying metadata as well. For example, if you do a copy file A to location B as file C, copy still has to pass the location and the metadata of the file to copy. So it's kind of, some commands are fit in all three categories. And when you take these considerations into account, you still have to think about, do you want to have a static order of the user emulation where, like, in every iteration, the same user emulation is executed? So what I mean by that is that the same commands are executed in the same order every time. Same goes for the arguments of the commands. Do you just supply some expected value to be there on the file system and let them be static, or are you randomizing the arguments as well as the order of the arguments? You can find some interesting results when comparing those approaches. And in my experience, I've tried that. And these are the results for successful executions of the user emulation commands for the static approach and the random approach. As you can see, the successful execution are actually always higher in the random approach, which makes sense, because if you define the static user approach in such a way that there's always a command in the first three that causes a crash, the others remaining commands are never executed. If you randomize the order, the order is obviously mixed, and you never know which commands are executed first, and then there's a higher chance of more commands being executed in total. For ZFS in particular, there's no change whatsoever. This has to do with the fact that the integrity checks and checksumming for ZFS are so strict that only these connections are put in place, that that only these file systems are getting mounted which are still valid. So if the ZFS file system is still valid, most of the commands are just executing fine. The 2% bad executions are because of bad arguments being rolled or some other weird side effects, but it has nothing to do with the actual ZFS file system being in a critical state. So one observation being made here is RNG seems to matter. And observation two, indirectly being made here, is that crashes do happen during mount, user emulation, and the teardown phase of file system fuzzing. So I'll come back to that a little bit later. But you have to take into account that when mounting a file system, the system can crash. When executing any of the commands defined, the system can crash. And actually, when destroying the block device, the file system is bound to, and the actual unmounting process, the system still can crash because of some weird side effects of written files to disk are not synced yet, and the file system structure is still so broken, and the system tries to unmount it, and then it just goes all bonkers, and the kernel panics. So next up, you want to do some monitoring of what you're actually doing. So obviously, if you're using VMs, you have to do permanent alive checks of all your fuzzers at all times, so the system runs somewhat stable. Obviously, you also want to do some tracking of samples, mutations, seeds, crashes, all the kind of stuff that later on helps you to analyze and reproduce the stuff you're doing. The third thing is the logging of the file system structure. As shown earlier, when generating the file system, I outputted some really verbose logging, which is saved as well, because this helps you to reproduce the same file system later on. And you actually can throw it in the script as well as a JSON file, and it just recreates the same disk later on as well. So you don't have to save all the actual disk images to your local hard drive, which is just like filling them out so massively. So saving the JSON logs of them is helping to decrease the bunch of stuff you have on a disk for when running the framework. And finally, you want to log the user emulation results. You want to log the commands that were executed successfully because those didn't have any effect. You want to log the user emulation commands that weren't executed successfully, because those failed for some reasons, which you can analyze later on. And you obviously want to log the command that caused the crash, because that's probably your proof of concept right there. Still, you have to take into account that it may just be that single command that caused the crash, or the combination of all prior executed commands plus the command that actually caused the crash. So there's the verification routine. Still have to make sure that this is all in place. So finally, I already talked about verification just now, so let's get right back to it. In my scenario, I implemented a very simple verification routine. It just periodically checks if there's a new crash in the database, then checks if this crash is unique. And in both cases, if that's not the case, we just wait and we do nothing. If there's a new crash and if it's unique, we fetch the saved user emulation logs and try to replay this exact file system on a separate instance, which is always fresh. Like after every verification, the OS state is reset. So there's like no weird side effects from mounting multiple file systems in the same system. And then if the crash is also happening on the always fresh instance, as I call it, it's verified that it always happens. One observation here is that OS side effects are not as bad as expected. So the results later on will show that most of the crashes I was able to find in my research are always reproducible. So like OS side effects from mounting multiple times, or like some weird background magic happen in the OS affecting the crash, is not really a thing actually. But anyhow, based on the hash, I said that my unit check is based on the hash identifier. So how does it look like? I've got an example here. Let's go to test cases core features. Okay, I've got 3 files in here. One Python script to extract core features and one actual core dumps, like at least the text representation of it. So if you don't add any diagnostic and debug features into the FreeBSD kernel and it crashes, the core dump kind of looks like this. You can see, okay, it dumped the core, when it happened, your OS version, the actual panic string, which is nice for logging, but not really hashable. Then some kind of GDB metadata, not really interesting. Okay, it's some reading symbol, not really interesting. Warnings we don't care about. Some other stuff we don't care about. And then there's actually a kernel debugger stack backtrace. And in here we have the actual execution chain that led up to the kernel panic. And in here you can see, okay, we have like some numeration and like some counter in the beginning. We don't really care about that either. What we really care about here is the static part of it, which is like the function and the offset. Those are static. The address is in here, and the add, we don't really care about that either, because the add is just random garbage we don't really need, and the address is variable. So when the system reboots and the same crash happens again, these addresses will probably be completely different, and hence our hashing will produce a completely different result. So we want to eradicate all of that and all of the following like garbage as well. So I'm only hashing these parts. I'll show you an example. So basically, we want to do extract core features and put in the default core log. And then I'm extracting this backtrace and just taking the static parts. And then I'm concatenating it to a string and hashing that one. And so I'm doing an MD5 and then char hash, and you can choose probably whichever, but both should be fine. But this gives us at least a pretty rough idea if the crash is unique or not. Because if the ordering changes or if there's some other stuff in here, the hash obviously changes too. And since this is my kind of unique feature I'm going for. However, if you compile in some diagnostic features into the FreeBSD kernel and the kernel, the core dump looks a little bit different, which you have to account for. In this case, this one is a little bit older already, but as you can see, it was done on FreeBSD 12. It was a page fault, then again, some GDB stuff we don't care about. A lot more metadata about instruction pointers, some fault code, like the supervisor tried to write data to a page that wasn't present. So hence the page fault. Like I said, some more metadata. And as you can see, the actual stack trace itself changed a lot too. So the static part we're looking for is at the beginning until here. And then there's a slash plus frame. And this part we don't really care about because here's again our addresses, which are variable. And there can be in the middle of it, can be like this kind of trap signal, which indicates also indicates some register values, which always obviously can be variable too. So in the end, we have the corresponding syscall causing the crash. So in this case, the malformed file system tried to create a directory at some path. I don't know yet right now, but it tried to access the file system which was mounted and write to the disk. And this caused the file system to try to write data to a page that wasn't present for some reason. So this is nice information for logging, but not really for hashing, since here like register values variable too. So again, we want to extract the backtrace and only take the static parts, which should always be the same. So these until the slash, and we want to get rid of the frame stuff later on. So if we do this, let's see if it's working. Yeah, exactly. So this is the cleaned up version of the backtrace. And as you can see, there's no trap signal in here. I got rid of that too. And then you can just concatenate this stuff and hash it again, and you get like your identifier for uniqueness. And that's pretty much it for the verification thing. So if you put all of these 5 steps together, how does it look like? Pretty much like this, I guess. It can be a little bit confusing, but all the things we talked about earlier are hidden here. We have the config file read at the beginning, then the test case fetching and generation, applying the mutation. Whoops. Transfer to the remote target system where it's getting mounted, and check if the system is still alive after mounting it. If not, the logs are saved and the VM is restarted. Even the verification on the right is put in place. So this is what it can look like when you try to write your own file system fuzzer. But obviously, since we're dealing with the fuzzer here, we're like, the obvious question in the room is, but can it produce crashes? Like so far, all of this was like pure theory, but now we're getting to the results. When implementing all of this, it can look like this. As you can see, it was like an early test run for 12 days early last year, and it has like over 80,000 iterations and stuff. And you can see in total, since starting it, it found like over 5,000 crashes and 32 new crashes since starting up this fuzzing instance on the database. The last panic it found is in UFS dearbed, which is quite common actually. Also, you can see like some additional more verbose metadata, like the last new crash was found at iteration 77,000, and right now we're like a little 4,000 iterations ahead already. So the file system being fuzzed here was UFS2, and like some metadata about mounts and executions. In this case, the iteration was being successful. The VM is still alive. The mounting was successful. The file system was being accessed, and 15 out of back then 22 program calls were actually successfully executed, and the unmounting was successful too. So everything was fine in this iteration, at least. As seen, others were not as successfully. So my findings with this approach were like pretty awesome, actually. When doing this for a little while, fuzzing for about 2 weeks or so, I was able to find over 100 unique crashes in the UFS and EXT implementation in FreeBSD. Among these were like multiple out-of-bound reads and out-of-bound writes, which means page faults. What amazes me is that there's still like super awesome kernel bugs like triple faults and double faults in both UFS and EXT in the kernel. If you don't know what these are, you should look them up. They are probably a nightmare to debug, but fun to find. A bonus crash I was able to find was a non-deterministic crash in the UFS file system, which when trying to verify, it always produced a different core dump. So I took the same mutated file system, applied the same user emulation it logged, and I tried it 6 times and I had like 6 unique core dumps from it. So this one is probably a nightmare to debug too, because you cannot really predict the behavior. So it's super weird. Anyhow, what I've talked about earlier too was the reproducibility rate, which is, in my case, over 80% of all the crashes I was able to find were reproducible and verifiable. So this shows that like OS side effects by not resetting the VM state to the same state before going to the next iteration is not really that necessary. At least it still produces good results if not doing that. Additionally, another 5% of the missing 18% have produced a different crash of verification, which means they're non-deterministic, which is, like I said, those bugs are like super weird and fun to look at, but a nightmare to debug. So only about like 12, 13% of all the crashes were not reproducible at all. Okay, and as I mentioned, like I've implemented 26 userland programs which deal with the userland relation. And from this 26 userland programs, I was able to cover 17 system calls that caused. So here again, the syscalls, which are like fun. For this 26 userland programs, as shown below again, I was able to cover 17 system calls, which you can see on the right now. Among these, there's like system mount, sysunmount, and a lot of different system calls corresponding to reading, writing, accessing, unlinking, like all the different stuff you can think of when dealing with file systems. So a pretty broad selection of all the things you can imagine, which shows that this approach is actually kind of useful in finding crashes among like different crashes in different file systems, because you can find a lot of different system calls, and your 17 system calls covered is still obviously not all of them, but it's a good start and a good approach to actually doing file system security, I guess. I've talked about randomization, and actually when randomizing the user emulation and the actual order of the commands being executed with each iteration, I was able to find 2 new system calls being covered with crashes. So with a static user emulation, where the programs were only executed in the same way, I couldn't find all of those. Same stuff with the extended emulation. I will go back a few slides. And here you can see a few of those userland programs marked with a star. I only added those in later on, which I don't really consider them useful. But as this bullet point shows, I was able to find 3 new system calls by extending the user emulation with these commands marked with a star. As I'm really getting short on time, I should hurry up, and you can find this all on the slides later on. And if you have questions, please reach out. But this brings us to 2 observations. Again, RNG matters and fine-tuning matters as well. So you fuzzing framework. So what is the result of this? I tried responsible disclosure with FreeBSD. I disclosed 50 from the over 100, like the most critical ones. And a bunch of emails later, I had 21 confirmed bug tracker numbers and 10, as of right now, 10 confirmed fixes in the upstream kernel. However, there was like no feedback or replies for months now, so I don't know if that's still a hot topic for them, but it still somewhat worked. Then again, since it was so successful on FreeBSD, I tried the same stuff to be on NetBSD and OpenBSD. Too long didn't read. They were not interested in their fixes, even though the kernel in their system showed the same behavior. It's utterly broken, in my opinion. But yeah, 0 fixes for both of them. So now quickly some caveats for the said a couple of times I was using fully fledged virtual machines. So FreeBSD is not the bloatiest operating system out there, but boot times are pretty bad when trying to fuzz. In this table, you can see the fat kernel is the default kernel being shipped with FreeBSD. And in my KVM virtual machines, there were like, on average, I needed 40 seconds for booting. When compiling in all these diagnostic options I had like the results for booting were obviously getting worse. So over 40 seconds on average. Then I tried to systematically throw out all the stuff I didn't need, like Wi-Fi drivers and legacy drivers and all that kind of shenanigans. And I ended up at least with a 10% difference to the fat diagnostic kernel, which is kind of fun. But the sad thing is the biggest improvement in boot times were like just getting rid of the 10-second boot delay, which is implemented so you can select like the boot mode in the bootloader, like single user mode, multi user mode, or diagnostic or stuff. So then again, when getting rid of those 10 seconds as well, it was on average like 27 seconds, which is not ideal, but I guess it's still way better than 40 seconds. So optimizing matters. Then again, boot times. If your system produces a crash, apparently since the new FreeBSD versions, there's netdump, which actually allows to transmit your like kernel dumps to a remote server when the system crashes, which would eliminate the need to reboot and fetch core details of your target system. However, this was super unreliable when trying it in my setup. There were like timeouts and stuff happening, so I didn't really dig into it any further. But it would be a cool addition to the framework. Another thing is like some kind of libOS, where you just plug in the necessary parts with your, like, instead of using a full-fledged KVM VM, would probably make up for a lot of like boot delays and stuff. But I didn't. Obviously, smart mutation. Right now, there's no restoring or recalculation of any checksums or integrity checks, which is super important for the X4 and ZFS file system, because they put those in place to have all those integrity checks and data integrity in place. Finally, implementing some kind of kernel feedback or kernel address sanitizer would be nice. But when initially doing this research, there was actually no kernel address sanitizer for FreeBSD. And I only just found out like earlier this month that last year in summer and for the Google GSOC, there were like a project for kernel address sanitizer, which was too late for money, but it would be fun to actually dive into that. Finally, like automatic deduction of metadata or field types and sizes to make the mutation and fuzzing even smarter, obviously. For scalability, since I've been using KVM VMs, it allows for easy automatic cloning, which is a pro. A Corners, it's kind of a fat VM, which takes up space and it needs some manual config adjustments. So end of file soon. What is the conclusion? Still today, write your own fuzzing tools, since the kernels still offer a lot of bugs that only wait to be uncovered. And modern file system implementations will need some more considerations when writing a fuzzing framework. As always, responsible disclosure can sometimes be a little bit frustrating, but in my opinion, this research was really worth it because I've learned a lot of new stuff about engineering. And finally, with the same breadth, file system allow for the deep introspection of userland to kernel behavior. So if you want to learn about userland and kernel-land behavior, picking something that's having the full execution chain from userland to kernel-land, like file system has, you learn a lot about the operating system. So that's it for me now. I still have one short demo to show you. If it's working, it takes like 10 seconds. Let's see if it's actually working. Then I'm done officially. Let's see. Okay, this is in place. If everything's working, we can see a nice little crash. But let's see. So I'm just executing my fuzzle here with like a -5 flag, which is just the flag for the proof of concept 5. And if you look on the right, there's like a monitor just showing the FreeBSD login interface. And I'm trying to mount and do a user emulation from a malformed UFS disk now. And if everything goes correctly, it should display some funny behavior at least. Let's see. Okay, there we go. Apparently it's pretty slow and it should go on forever, but the video is kind of hanging. But this one actually goes on forever, like the page faults were just running off the screen and never ending. But as you can see, this is like I created a block device, I mounted the file system, and then did some emulation in the background, and it did a page fault right at the start. If you want to see how it looks like when it's not stopping, I can show you a demo later. But yeah, that's it for me. If you have questions or suggestions, please reach out. I'm available on Twitter, like Nalsec, or like via email. Scripts and slides will also be on my GitHub, so feel free to check them out. And if there's any questions now, I'm happy to take them.
Well, we are very short on time. There was one question that asks, are you releasing any fuzzing tools? Is that the scripts you mentioned at the bottom?
The fuzzing tools for the right now for the lab or like the talk, these are like the scripts I shown earlier. For the fuzzing themselves, I wrote a fully fledged fuzzing framework which does all of that automatically. I will be releasing that later on as well in the repo shown here on the last slide. But if you want to play around and try file system fuzzing, the scripts will be enough for now.
Okay, thank you very much. This is very much all we have time for. Thank you for an amazing talk.